Hello, my name is Claudio Kozický and I'm from the Faculty of Information Technology of the Czech Technical University in Prague. I'm presenting a paper called Space-Efficient KD Tree-Based Storage Format for Sparse Tensors. In many application areas, tensor computations involve very large sparse tensors. Before the actual computations can take place, it's often necessary to pre-process the used sparse tensors. For example, the sparse tensors first need to be loaded from the used storage medium to the computer's memory. In the process, it may be necessary to decompress the sparse tensors file. It's also oftentimes necessary to convert the sparse tensor from the storage format to an internal format which supports the desired calculations. If the sparse tensors are very large, these pre-processing steps may take a considerable amount of time. For this reason, it's desirable to decrease the sparse tensor sizes if possible. For this reason, we present the succinct KD tree-based sparse tensor format, and we compare the space requirements of sparse tensors stored in this format with existing tensor storage formats. We demonstrate the computational efficiency of the SKTB format for parallel sparse tensor vector multiplication. We also present a parallel algorithm for converting sparse tensors to our SKTB format. When we refer to a tensor, we have in mind a multidimensional array which has at least 3 dimensions. When we refer to a sparse tensor, we have in mind a tensor which contains enough zero elements that it is advantageous for performance or storage reasons to only store the tensor's non-zero elements. Existing sparse tensor storage formats can be divided into two groups: internal formats, also called processing formats, and external formats. Internal formats are optimized for executing sparse tensor operations. This means that it's usually not possible to store a sparse tensor to a file using an internal sparse tensor storage format. On the other hand, external sparse tensor formats are used for storing tensors into files, but after loading the sparse tensor, it's necessary to convert it to an internal format to perform the desired calculations. We have observed that a space-optimal sparse tensor format, which can be used simultaneously as an external and an internal format, isn't available. But our sparse tensor format can be used as an internal and external sparse tensor storage format. Our format focuses on compressing sparse tensors' structural information. This means that we don't compress the sparse tensors' numerical values, or to be precise, the non-zero numerical values. Generally, the numerical values can be compressed using a general-purpose lossless compression algorithm, and additionally, it's usually possible to decrease the precision of the calculations to save even more space, but this isn't investigated by us because it's domain specific. We call our sparse tensor format the succinct KD tree-based format, or SKTB for short. The internals of our format are based on the idea that a sparse vector can be represented using a binary tree. For this to be space efficient, it's better to use the succinct binary tree format. Our format extends the SBT format to support representing multidimensional data of sparse tensors. Specifically, the SKTB format splits the stored sparse tensor into equally sized halves along the sparse tensor's dimensions. This approach is also used by KD trees. We also present a parallel SpTV algorithm for performing sparse tensor vector multiplication with tensors in the SKTB format. SpTV is sometimes denoted as the M-mode product of the tensors. In other words, this means that tensor A, which is d-dimensional, is multiplied along its mth dimension with input vector x. The result of this is an output sparse tensor which has d-1 dimensions. Our parallel SpTV algorithm computes the resulting numerical values of the output sparse tensor and also its structural information. When SpTV is repeatedly executed with the same input sparse tensor, for example in iterative algorithms, it's possible to reuse the structural information in subsequent iterations. We tested our format using 8 domain-specific sparse tensors from the formidable repository of open sparse tensors and tools. The table shows abbreviations of the tensors which we use to further refer to them. It also shows the non-zero element count of the sparse tensors and the sparse tensors dimensionality. We compared the space requirements of storing a sparse tensor in our format, and we compared it to the space requirements of existing sparse tensor formats. The results showed that when we compare our format to HOCOO, a commonly used internal sparse tensor storage format, then our format is 5 to 17 times more space efficient. When we compared our format to commonly used external sparse tensor format, then we could see that our format is usually more space efficient. We also measured the performance of parallel SpTV using sparse tensors stored in our format and compared it with the performance of SpTV using a state-of-the-art library called ParTI. The results showed that even though our format wasn't primarily designed to maximize the performance of parallel SpTV, the performance with our format almost matches that of the ParTI library. Finally, we tested the time it takes to load a sparse tensor from its file and perform all necessary pre-processing steps to have it prepared for any calculations. We tested internal formats and external formats. The test results showed that using the SKTB both as an internal and external format is the fastest out of all available possibilities. To sum everything up, we have presented SKTB, a space-efficient storage format for sparse tensors. In the paper, we present an efficient and scalable parallel algorithm for SpTV and a parallel algorithm for converting tensors from the HOCOO format to our SKTB format. The results showed that as an internal format, SKTB is several times more space efficient than HOCOO, a commonly used internal format. As an external format, SKTB enables loading tensors faster than existing formats. Therefore, our SKTB format represents the best trade-off between external and internal sparse tensor formats. Thank you for your attention.